Welcome to my video. I'm going to do a book review of this book, Quantum Theory, a very short introduction by John Polkinghorne. This is an Oxford book, and these are nice little short books that kind of introduce you to a subject. I've read several other different ones. I want to go over this one today. These are all the different books in the series, quite a few of them actually. And so let's just get started on this. We'll talk about, I'm just going to highlight some of the things that jumped out at me. And here's a famous quote. I think I can safely say that no one understands quantum mechanics, by Richard Feynman. He's a famous physicist that said that quantum mechanics is not intuitive, is basically what he meant. Here's our table of contents. And first of all, let's talk a little about this John Polkinghorne. He studied under Paul Dirac, which is a famous physicist that helped set up much of quantum mechanics, so he comes with quite a pedigree as far as his educational background. And from what I've read of the book, it's really good. It's a good introduction to the subject. Classical crack. So this first chapter talks about the breakdown in classical mechanics and how quantum mechanics evolved from it. And so around the turn of the century, in late 1800s, they thought they really understood physics, until they started getting into this black body radiation, trying to understand that. That's where things started breaking down. And so at the bottom of these pages, sometimes you'll see a little notation like Maxwell book, Amazon. Okay, that refers to a book I've got on Amazon about James Clerk Maxwell. You're welcome to get one of those if you want. And I'll also have certain things where I show a video reference at the bottom. I'll get to that in a minute. I'm not going to explain all these, but that just shows you I've got a video on the Math and Physics Learning channel if you're interested. So James Clerk Maxwell, he developed the theory of electromagnetism that we still use today. He was on level with Einstein and Newton, basically. And then they started looking at all these different spectra of emission spectra, like of different gases, and they had all these lines in the spectra they didn't understand. And so it became a problem trying to understand those. That kind of helped evolve quantum mechanics. And so Max Planck, he was working on this thing called the ultraviolet catastrophe. And that's basically where they didn't understand the energy distribution coming out of a black body radiator. That's something that's it's a perfect radiator, and theoretically. So Planck was a professor of physics in Berlin. I'll see videos. I've got a video on that, two of them actually, I think. And so then this is around the year 1900 to 1905, the early 1900s. And then we've got Albert Einstein gets involved, and he's using this idea of the quanta, which Planck developed to understand this photoelectric effect. And that's where electrons were emitted from a metal that is irradiated by light. And they didn't fully understand why the level of the intensity of the light and then the just how that all worked. So then we move into Ernest Rutherford, and he was a New Zealander that moved to, he lived in Canada and the UK, and he studied the atom and came up with a model of the atom that was fairly close to what we have today. At least it had a central atomic core of a positive charge. And then we have Niels Bohr, who worked with Rutherford at Manchester University. And Bohr was a theoretician, whereas Rutherford was an experimentalist. And Bohr came up with what's called the Bohr atom. It's a basic model of hydrogen, and it worked out pretty well. It explained a lot of the spectra of the atom. And then the light dawns. So this talks about where the quantum mechanics is starting to form. A few years following Max Planck's pioneering proposal was a time of confusion and darkness in the physics continuum. Light was waves, light was particles. Tantalizing successful models, such as the Bohr atom, held out the promise of a new physical theory was in the offing. So this is really the development of the early stages of quantum mechanics. Here's a bunch of the famous scientists it's called the Sauvé conferences. They had a series of those. I think it was in Brussels, and it was sponsored by a big industrialist named Sauvé, and all the scientists and physicists came together to try to understand. That's where a lot of quantum mechanics came together. Heisenberg was one of the big names in here, and he developed what's called matrix mechanics. It's a mathematical method of looking at the quantum phenomenon. And so he developed that, and he came up with the uncertainty principle, which is really important. And so quantum mechanics, here we got Paul Dirac, which was one of the author's mentors in Cambridge, and he developed a lot of the things. He really developed a lot of quantum mechanics. Okay, and then one of the famous experiments was a double slit experiment that they did that with light back in 1801, and they understood that, at least in classical. But then you start running electrons through it, and it breaks down individual photons. So that kind of helps shed light on this, the quantum phenomenon. And so quantum theory deals with probabilities rather than certainties. So then we start getting into this probabilistic approach, looking at nature and quantum mechanics. And then we've got observables. That's where certain things can be observed, and it changes it's called the wave function. It collapses the wave function. So I've got videos on this, on vectors. We start talking about vector addition. Vectors are important to understanding quantum mechanics, and one of the fundamental things to understand. We talk about operators that work on these wave functions, and I'm just touching on this real quick. Let's see what we've got here. Keep going on. Okay, the uncertainty principle. I mentioned that a second ago. Got a video on that also. This has to do with the Heisenberg uncertainty principle, which really gets down to some of the basic things in quantum mechanics. We can't know the momentum and the position to any arbitrary accuracy, and that's called the uncertainty principle. Probability amplitudes, this got to do with wave functions. And this doesn't really go into the math on this, it kind of gives a conceptual idea. So if you're not up on the math of quantum mechanics, don't worry about it. This book kind of steps you through some of the basic ideas. Quantum logic, this is big in quantum computers now, as they develop those. Darkening perplexities. Now this is where things started getting, like that first statement I showed you at the beginning, where nobody understands quantum mechanics. What happens is it becomes, the classical ideas break down, and the way these physicists understood things became very confusing. Einstein really jumped in the mix, and he didn't really like all those probabilistic approaches. Okay, decoherence. This is a problem. Basically, a quantum mechanics starts to break down in the macroscopic world, and so that's decoherence. That's why random motions in the just the environment break down the quantum mechanical effects. Let's see, the measurement problem. Yeah, anytime you measure something, it causes this collapse. And then this, whether this is the Stern-Gerlach experiment, you shoot a beam of electrons through here, a non-homogeneous magnetic field, you get up and down, two divisions. It's got to do with the magnetic spin of the electrons. That was a famous experiment. Let's see what else we've got here. Oh, large systems. Oh, quantum mechanics items do not have definite properties until measurements. Yeah, exciting in the separation of the possible states. This has got to do with the measurement problem. Basically, you don't know what you got until it's called collapsing the waveform. And then you get a measurement, and it gets all kinds of odd things on this. It'll wrap your head around it. Schrödinger's cat, that's one of the famous Erwin Schrödinger sends a letter to Einstein explaining this experiment of a cat in a box, and it has to do with the possible waveforms of the cat being living or dead. It's a problem that's been talked about for years. Determinism, let's see. Chapter 4, further developments. Okay, this goes into tunneling, and I remember that was my senior project. As a physics major, I did an experiment on that and tried to explain that, and that was pretty neat. It involved liquid hydrogen, and that was interesting. It's where, in the classical world, a wave going up against a barrier, some kind of potential barrier. Think of it as a car trying to go up a hill. If you don't have enough speed or energy to go up that hill, you can't make it over it. Well, in quantum mechanics, there's a certain probability this electron or wave function approaches this potential barrier. The analogy of a hill, part of it will make it through. And so that's called tunneling. And it turns out to be a very important effect as far as the generation of energy in the sun due to nuclear fusion. So it just briefly touches on that idea. Well, let me turn this page here. Okay, then it talks about statistics, and let's see. Oh, the Pauli exclusion principle. This is very important because this is how the periodic table develops, because it's got to do with the way electrons pack, and this gives you all the properties of insulators and conductors. So that is how we have chemistry. The band structure, it talks about the way the electrons form around an atom. You get different for an insulator and then a conductor, the way the electrons form. Lane choice experiment, and those are kind of complicated. Sums over history, let's see. Oh, Richard Feynman discovered an iconoclastic way of reformulating quantum theory. So a lot of physicists, including Einstein, didn't really like this initial quantum mechanical way it was developed. And a lot of physicists over the years have come up with alternate solutions. But we've just stuck kind of with the basics that came out of it. It tends to be the way things are going. Relativistic quantum theory, so this combines relativity, which Einstein developed, and quantum theory for things going really fast. Quantum field theory, this has to do with electromagnetics, when you're dealing with electromagnetic fields, the association with quantum mechanics. And so that is another area of quantum mechanics that deals with electromagnetics. Quantum computing, this is a big deal. The world's moving towards this. These quantum computers, I'm learning about those more. Basically, they work extremely fast. From what I've read, you could do a calculation that might take you months to do on a regular computer, a regular supercomputer, whatever a regular supercomputer is. It may just take seconds or minutes in a quantum computing, but the only problem is you have this decoherence comes into effect, and you have to have some very cold temperatures and really complex technologically, even though it's extremely fast, but these are in the work. Togetherness, this is where the ideas started to come together. Let's see. The quantum entities that have interacted retain a power, mutual influence over each other. Okay, this has got to do with entanglement. This is where things get really, this has to do with Einstein. Back in 1935, he came out with this paper called the EPR. That's Einstein, then two of his collaborators, I forgot their names, one started with a P and one started with an R, had this idea of once particles interact, that they maintain some information about each other. And this is where Einstein was quoted saying a spooky action at a distance. That's where that quote kind of originated in that time frame. And then chapter 6, lessons and meaning. This is a more philosophical approach to understanding quantum mechanics because it deals with reality and causality, and this is where philosophy and physics kind of meet. And this kind of gives you some overview of what's going on. People trying to interpret quantum mechanics in the real world that we live in. So it's a pretty short, it's very definitely a short book, and the title says that, and but it's really compact and gives you some good information. You won't be an expert, but you'll have a general idea of what's going on. Got a glossary of terms, and I looked up some of these terms back here that just to make sure I understood exactly what they were. And then, here's a mathematical approach. This is kind of a quick summary of quantum mechanical math. And if you're mathematically inclined, and a background on this, you can kind of look at this and it kind of ties some of this together. Because I know if you understand the kind of the mathematics, some of these conceptual ideas seem complicated, but you see an equation, it just makes sense. So this is, it just ties it together quickly. Some of the overview of the math involved in quantum mechanics. So that's a good little thing to look at. All right, well, there you have it. I hope you got something out of it. Basically, in my opinion, it's a darn good book. You'll learn a little bit about quantum theory. Won't be an expert, but it's a good place to start. Thank you for watching.